Computers store data, but how they store it changes everything. An array stores elements in contiguous memory, one after another with no gaps. Each size is fixed when it's created, so you can't resize it later. An array stores only one data type, such as integers, strings, or booleans. Whether this rule is strict depends on the programming language. Elements are accessed by their index, starting from 0. This gives you direct, constant time access. Appending an element to the end is usually efficient, but inserting an element in the middle means every following element has to shift one position to the right. Deleting an element from the middle works the same way. Every following element shifts one position to the left. And here is time complexity summary. Okay, that's a quick summary of everything we cover about array. Feel free to pause here and take a screenshot for future reference. A linked list is a chain of nodes. Each node stores a value and a pointer to the next node. Unlike an array, nodes aren't stored in contiguous memory. They can be scattered throughout memory. Every linked list starts with a head node. Without the head, you can't access the rest of the list. To reach any node, you start at the head and follow the pointers one node at a time. There are three common types: singly linked, each node points to the next node; doubly linked, each node points both forward and backward; circular, the last node points back to the head. Insertion and deletion are a fiction, because you only need to update a few pointers. But searching is always linear, since you may have to traverse the list node by node. A stack follows the LIFO principle: last in, first out. The last element pushed onto the stack is the first one popped off. Only the top element is accessible. Everything below it stays hidden. There are three basic operations. Push, it means adds an element to the top. Pop, it means removes the top element. Pick, it means returns the top element without removing it. Stacks are commonly used for function call stack, undo systems, and expression parsing. A queue follows the FIFO principle: first in, first out. The first element added is the first one removed. Elements enter from the rear and leave from the front. There are two basic operations. In queue, adds an element to the rear. Dequeue removes an element from the front. There are several variants. A double-ended queue or dequeue allows insertion and deletion at both ends. A priority queue doesn't follow FIFO. Instead, the element with the highest priority is removed first. Queues are commonly used in task scheduling, data buffering, and BFS. A hash table stores key-value pairs. A hash function takes a key, computes an index, and stores the key-value pair at that index. The same key always produces the same index. That makes lookup fast, with no need for a linear search. The challenge is collusion. Sometimes different keys produce the same index. One solution is chaining. Multiple key-value pairs are stored at the same index using a linked list. Another solution is open addressing. Instead of using linked list, it searches for the next available slot. On average, insertion, deletion, and lookup all run in O1. In the worst case, if there are too many collusions, they degrade to ON. A graph is a collection of nodes connected by edges. Unlike a tree, a graph has no hierarchy. Edges can be directed, pointing in one direction, or undirected, allowing movement in both directions. Edges can also be weighted, where each edge stores a value such as distance, time, or cost. There are two common ways to store a graph. An adjacency matrix uses two-dimensional array. It provides O1 edge lookup but requires big O of n squared space. An adjacency list stores neighbors of each node. It uses much less memory and is more efficient for sparse graphs. Graphs can be traversed in two main ways. Breadth First Search, or BFS, explores the graph level by level. Depth First Search, or DFS, explores one path as deep as possible before backtracking. Graphs are widely used in social networks, maps and navigation, recommendation systems, and network routing. A tree is a hierarchical data structure. It starts with a single root and branches downward into nodes. Every node has one parent, except the root. Nodes with no children are called leaves. A binary tree allows each node to have at most two children, a left child and a right child. A binary search tree, or BST, has one simple root. For every node, values in the left subtree are smaller and values in the right subtree are larger. Because of this rule, searching takes O log n on average. At each step, you eliminate about half of the remaining nodes. But if the tree becomes unbalanced, a BST decreases to On. That's why we use self-balancing trees. There are three common ways to traverse a binary tree: in order, pre-order, post-order. In order: left, root, right. On a BST, this visits the value in sort order. Pre-order: root, left, right. Commonly used to copy or serialize a tree. Post-order: left, right, root. Commonly used to delete a tree. And that's a quick overview of the most important data structures every programmer should know. In the next videos, we'll explore each one in depth with real code, step-by-step operations, visual animations, and practical examples. If you found this video helpful, don't forget to like, subscribe, and turn on notifications so you won't miss the upcoming tutorials. Thank you for watching, and I see you in the next video.